Hello, and welcome to Organic Chemistry. This playlist of 5 to 10-minute videos are designed to give you just bite-sized chunks of organic chemistry to take you through the entire subject semester without choking. And today I'm only going to ask you to remember a few things from general chemistry, and then we'll be ready to dive right in to the beauty of organic. And the first thing I'd like you to notice is this periodic table that's been condensed and simplified. These are all of the atoms I'm going to be talking about this semester almost entirely. We don't need heavy metals right now. All we need are these 3 rows from the top of the periodic table. And I want you to notice something about them because the periodic table is organized in a very special way. And we want to remember that because it's going to make life very easy for us. The first one is that these energy levels are represented by rows. E1, E2, and E3. Atoms very much behave specially depending on the energy level they're in. And when you look at the columns in a periodic table, if you remember from general chemistry, a lot of the behavior can be predicted by where they are. Sulfur and oxygen, for instance, are in the same column. They're going to have a lot of similar behavior in similar situations. It's just that the ones that are lower are heavier. Phosphorus here has a lot of similar places in nature as nitrogen is found, but they do behave just a little differently because each one of these elements has their own personality. So just remember that energy levels are very important. And if I look at the far side here, in fact, let's come back. Let's get a pink color out. Can I do pink? Let's do some pink. Look over here on the right side. I want you to remember this 2, 10, and 18 element number, because the reason these elements are on the far right side is that those are the number of electrons necessary to complete an energy level and move on to the next row. When something like helium, who has 2 protons and 2 electrons on average, forms this s orbital, and it's called that because it's spherical, s for sphere. An energy level is completed at that point. This first energy level is now completely full. So helium forms this kind of candy-coated protection shell here that makes it impenetrable. It's so hard to split helium up because these electrons are just the right number to the number of protons in the center helps, but it's really the number of electrons here, where they can find a perfect frequency and harmony with which to oscillate and whip around this nucleus without getting in each other's way and getting lots of time exposed to the protons in the center as best they can. So if I move up an energy level, like if I take neon for instance, the first energy level is going to be completed. That much is a given. 2 electrons are all he needs for that, and neon has 10 protons, so he's definitely going to attract more electrons than that. So let's just remember here that that 1s orbital is full. So I'm going to give a little yellow squiggly line here to show that. This is not what you might call standardized chemistry. But come over here and look at what starts to happen on the second energy level. Let's look at all the electrons fill in on this as we go forward. Lithium, with only 3 protons, already lives in the second energy level, and he's going to try to fill an s orbital, another spherical orbital. He has room here for 2 electrons. Every orbital has room for 2 electrons, so notice here how we have these 2 elements living in their own kind of subsection here on the second energy level. It's exactly for this reason. Lithium and beryllium are working to fill this s orbital. Lithium only has 1 here, but beryllium will fill in over here. And once you do that, notice here we have a group of 6. Do you remember this from general chemistry? It's okay if you don't, but I want you to picture a tetrahedron, like a 3-dimensional construct here like this. We'll build a triangle out of it. And think of it in 3D. In each one of these directions, I'm going to draw a balloon. And the reason I drew it ahead of time is because I'm bad at drawing balloons. But I want you to think of it kind of like that. That one sucks too much. Let's fix it. Okay, something like this. Each one of these orbitals has room for 2. And as you move to the right on the periodic table here, boron, carbon, nitrogen, oxygen, well, our neon has more protons than all of them, so we're hoping it'll attract more electrons. But remember that electrons fill in as far apart as possible because they repel each other. They're all negatively charged. Surely you remember at the center of the atom is where all our positive protons live, and our neutrons, which have no electrostatic charge, right? And they live in a 1/1,000,000th the size of the actual atom, even in the first energy shell. Very tiny microscopic dot in the center of all of this is where every one of those protons lives together, compared to where these electrons are whipping out to. But we still don't have enough of these to get to neon's representation here. So now that we have one electron in each orbital, we can put a second one in each one of these. And as soon as we complete all of these orbitals, they find a fantastic harmonic behavior. It's very low energy compared to just some of these orbitals being full. I know it sounds counterintuitive, but then it forms this completed second energy level. And nothing's going to want to come through here. Nothing's going to want to exit. Nothing's going to be able to enter. These electrons are whipping around in here in a way that keeps this very, very good at repelling new electrons. They don't have room for anyone else, and they're very happy with where they are because they each take turns finding their way as close as they can to the center here. Now, getting through that first energy level is almost impossible again, but these electrons are going to find ways to kind of whip around like this and whip around like this, like comets orbiting the sun. But there's enough of them, and their electrostatic behavior, all these negative charges, are going to repel other electrons wanting to enter this energy level. They're going to be fine if other atoms want to be nearby, if another neon were to show up out here or something like this. But his electrons are busy living inside his own second energy level candy shell. So for today, I want you to remember that part. Let's just do one other little thing while I'm being greedy with our first lesson here. I want you to think about someone like lithium, who lives in a different and an uncomfortable situation. So I've got 3 protons in the middle, but we just write it like this: lithium. He's going to complete his first energy shell with his first 2 electrons. They will fill that in, and I want you to picture that first energy level as being complete, right? And now we're moving down to the second energy level where lithium lives. He's going to have another spherical orbital try to show up, with 1 electron living here and 1 open space here. And now I want to look at fluorine, who's going to have, let's draw the F a little smaller than that. Look at fluorine, who has 9 protons. That's a lot of positive attraction. He is going to have that same first energy level filled, and he is going to have enough positive attraction to be able to hold more electrons nearby, so that 2s orbital, of course that's what we call it, it's the second energy level and it's spherical, is going to fill. And then these p orbitals, these balloons, are going to be mostly full. We're going to have 1 here, 1 here, 1 here, and of course they're trying to avoid each other while trying to be close to the nucleus at the same time. But I want you to notice that fluorine only needs 1 electron to complete the second energy level. He lives so close to neon. God, what he wouldn't give to be as stable as neon. And lithium out here, his last completed energy level is right here. That's energy level 1, right? Fluorine's energy level 1 is here. Same idea, just that 1 spherical shell. But neither of them have completed their second energy level. But as these electrons are whipping around, this electron here is very interested in saying goodbye to lithium. He's not able to really penetrate that first energy level, and lithium only has 1, 2, 3 protons. That's not a lot of positive attraction. Not a lot. Not when there's an energy barrier here. This last electron is invited to the party, but he's kind of hanging out in the corner. And fluorine has freaking 9 positives in the center. That's a lot of strong attraction with only that same one energy level barrier. It's very easy to see this electron find his way to this open space here. And when he does, he's going to fill this spot, and fluorine's going to go, oh snap, I just completed my second energy level, and now I'm going to build this protective shell. And lithium's like, do it, take it. We don't even like that guy. He's gone now. And that allows lithium to shrink down to a smaller size, just that completed 1s orbital. And more importantly, because he has 3 positives and only 2 negatives, it leaves him with a net +1 formal charge. I should say total charge. We'll talk about formal charge later. And fluorine is left with a -1 total charge here. So even though that this lithium has donated his electron and now he's condensed down to a very well protected couple of electrons, these positive and negative total charges attract each other. And that's exactly how an ionic bond works. Something like sodium chloride, table salt, as you may well know, when you pour it in water, it's able to just fall apart. Well, that doesn't happen with like nitrogen gas, which is our atmosphere, 70% of it. You don't just put air in water and see it stay there. Because atoms that share electrons are very different than atoms that donate electrons. And in this case, these electrons are donated. And it's based entirely on the attraction to the available electrons in the outer energy shell here. So today, just remember these few things. The first is these energy levels are very important. The second is that anything in an energy level higher up, or lower, I should say, lower energy level, completed, is going to be inaccessible. Anything inside the energy level 1 here for an energy level 2 atom is really not going to be available to you to play with. And the last one is that ionic bonding happens when electrons literally donate themselves to someone else, and then the remaining charges on the atoms are what attracts them to each other, to sit shoulder to shoulder. They're not glued together, but they are willing to stand shoulder to shoulder because they complement each other. Keep track of your spot in class by using the full playlist here, or click next video to continue.